next topic we're going to cover is testing a claim about a mean. We've started dealing with hypothesis testing already. All right, we're going to start the new stuff. Testing a claim about a mean. So the key concept is that we are dealing with the population. So the objective is to use a formal hypothesis test to test a claim about the population mean. And the population standard deviation sigma is not known. The population standard deviation sigma is known. What do we mean by that? There are two possibilities, and we want to pay attention to that. Either sigma is given or sigma is missing. Population standard deviation.
The z-test is a statistical test for the mean of a population. It can be used when n is greater than or equal to 30, or when the population is normally distributed and sigma is known. The formula for the z-test is test statistic. Z is equal to x bar minus mu over sigma times the square root of n, where x bar is the sample mean, mu is the hypothesized population mean, sigma is the population standard deviation, n is the sample size.
So when do we do the z-test? The key being sigma is given, and that's why it's important. As we read the question, we should write the given accordingly, symbolically, so we know whether sigma is given or not, and therefore we use the z-test or not. Of course, we can always use technology. You need to know the steps and go through the process, and if need be, you can always use technology.
The t-test is a statistical test for the mean of a population. It can be used when n is greater than or equal to 30, or when the population is normally distributed and sigma is not known. The formula for the t-test is test statistic t is equal to x bar minus mu over s over square root of n, where x bar is equal to the sample mean, mu is equal to the hypothesized population mean, sigma is equal to the population standard deviation, and n is equal to sample size.
So what is important here? The key is sigma is not given. And of course, S is the sample. And normally, sigma is missing. You can use technology to get to the answer. Before that, you really need to know the steps, as I mentioned before.
Confidence interval and hypothesis testing. When the null hypothesis is rejected, the confidence interval for the mean using the same level of significance will not contain the hypothesized mean. Likewise, when the null hypothesis is not rejected, the confidence interval computed using the same level of significance will contain the hypothesized mean.
There were three different methods that were discussed. We will look at those, and we will look at some examples to make some sense out of those. Each one will be discussed accordingly. Traditional method, p-value method, and now confidence interval. So when you set up a confidence interval, either it contains the value from the null hypothesis or it doesn't. That's the idea, and you can distinguish between the two accordingly.
The number of hours of sleep for 12 randomly selected adults subjects are listed as 4, 8, 4, 4, 8, 6, 9, 7, 7, 10, 7, 8. A common recommendation is that adults should sleep between 7 hours and 9 hours each night. Use a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. Assume a normal distribution.
Let's see what's given. As we look at this question, obviously we can count, okay, or we can look at this number, and this is it. There are 12 pieces of data. Alpha is 0.05. What is it that we are testing? Use a 0.05 significance level to test the claim that the mean amount. See, you really have to pay attention to this, because this tells you what is your test. So your test involves mu of sleep for adults is less than 7 hours. Less than 7 hours. So right away that means mu is 7. Okay. Now, as you can see, population standard deviation is not given. Okay. Also, we are assuming what? Normal distribution. We are assuming normal distribution. Okay. We are assuming ND. So what do? We know how to calculate the mean and standard deviation of any sample. For the sake of argument, in a case like this, we put it into technology, and it gives us the answer. I'm assuming everybody can calculate those. Just in case, of course, the formula I'm going to remind you, x bar is summation of x over n. So you can add them up, divide by size, which is 12. And s is the square root, x minus x bar quantity squared over n minus x minus x bar. Can be done by hand, we can do it by technology, so therefore here's the given. We are dealing with the normal distribution, n is 12, alpha is 0.05, mu is 7, and technology results in x bar and s as follows. It's important to see sigma is missing, and so the very first step is h0 and h1. You said the question is asking for the amount, the mean amount, so mu. So mu is less than 7 becomes h1 or the alternative. So h0 is equal to that. And I hope you see that according to the question, what is it that we are testing? The claim that it's less than 7. So h1 is not only a left tail test, it is also the claim here. Okay. Now, the next step is the calculation of test statistic. So I want you to pay attention to the bottom left in blue. I have given you the steps. The first step is done. The second step, you have to use test statistics. So you use your formula sheet and you see the formula at the very top, and you simply plug in t is equal to x bar minus mu over s over square root of n. Everything is found. Plug in, calculate, negative 0.290. The third step involves critical value. Critical value comes from the choice of alpha. Alpha is given as 0.05. This is using the t distribution because sigma is unknown. So we need degrees of freedom, which is n minus 1. And the table. By now, I think we are sort of comfortable with using the table. It results in t being negative 1.796. And so all you have to do, compare these two numbers by looking at the graph. So here's the graph. Alpha is 0.05, critical value of negative 1.796. And test statistic is larger than that. It's to the right of it. It's way into the non-rejection region. Non-rejection region. Therefore, what? Do not reject H0 or fail to reject H0, whatever. Now, when you do not reject H0, in essence, you are rejecting H1. In essence, you're rejecting the claim. In essence, you're saying the claim is false. And now you do the simple writing. So you are going to say do not reject or fail to reject H0. The claim is false accordingly. I hope everybody understands why it becomes false. And the wording, you just use the universal wording. There is, or in this case, there is not sufficient evidence to support the claim that the mean amount of adult sleep is less than 7 hours. Again, this is according to the data. And needless to say, it's a small data, but that's the idea behind the test of hypothesis. We want to find something about the population, and we use sample. We can use the p-value method, okay, just for the sake of illustration. By the way, one is good enough. You don't have to do all three, but for the sake of illustration. When it comes to the p-value, I want to explain that here. The idea is that if I'm interested in finding the p-value, I'm interested in looking at whether it's left tail test or right tail test first. Obviously, this is a left tail test. Therefore, it's to the left of a test statistic. So if I'm looking at this one, Right now, with the traditional method, what did I do? I compared, look at step 2 and 3. I compared two numbers, okay? I compared number negative 0.290 and number negative 1.796. P-value does what? Compares the area. So look at the alpha of 0.05, okay? You can see the region, the green shaded region of 0.05. Now, the p-value says, in this case, because it's a left-hand test, to the left, the area to the left of your test statistic, okay? All right, so negative 0.290, if we were to look at this whole thing would be considered your p-value. So what are we doing here? We are comparing two areas. One area is alpha equals 0.05. One area is the p-value. When the p-value is larger than alpha, we are way into the non-rejection region. So do not reject H0. In other words, you better get the same result. But it's important to see how it works. Again, traditional method compares to numbers, p-value compares to areas. So here's the p-value. Again, when you do the technology, by the way, you can put in the information. I've given you this stuff up there so you can see how that works. So you plug in and notice the p-value when you go through the technology. And the reason I mentioned that, because especially in the case of a t-table, the table is extremely limited, but you can have an idea of what's going on. But from here, here's your p-value, which is clearly larger than 0.05, and therefore do not, you get to the same result. Do not reject HC. Okay, it's way larger than alpha, which was again 0.05. Now, this is a left-tail test. T test statistic was negative 0.290, and so the p-value is the area to the left of that, and so we found that to be 0.3887 or so as far as the technology is concerned. If we were to look at the table, it tells us that the p-value, and we will look at the table in a moment, I'm going to show you that. Degrees of freedom is 11, 0.290 is less than all of the listed t-values in the row, so the p-value becomes larger than 0.1. We will look at it in a moment. I just want to finish this since the confidence interval, I want to discuss that as well. So we get to the same decision. P-value is 0.3887, larger than alpha of 0.05, and you make the same decision. As far as the confidence interval, everybody has seen that before. We have done that, so I don't want to go through that again. We just use X bar and we add and subtract E. Now, what is E? E is T alpha over 2 S over square root of N. Now, so we have everything from the previous page. The only thing I want to add, remember, it says 90% confidence interval. I want to discuss that. Why 90%? So remember, this was a one-tailed test, everybody. And so if it's 5% to the left or to the right, makes no difference in one side. If you want to compare it to the proper choice of confidence interval, then your confidence level must be 90%. And here's the reason. Let me do the drawing for you. So we had, from the previous page, this area was 0.05 and it was a left-tail test. Now, if I want to look at an equivalent confidence interval, I need to put 0.05 on the right, which results in a 90% confidence level. And therefore, I get exactly the same T that I got over there for the critical value. In other words, the T that is used here now, this T is the same as the t we had in the previous page. Now remember, with the confidence interval we have plus minus, so you just use the plus and you do the work. So when you go through the process, it will result in the following: the t interval 5.8004 to 7.8662. So what happens here? We are 90% confident that this is the interval that contains the true population mean, so you cannot reject H0 according to this calculation. The range of values in this confidence interval contains mu equals 7 hours, so we are 90% confident that the limits of 5.8004 and 7.8662 contain the true value of mu. The sample data appear not to support the claim. In other words, we do exactly the same thing as we did in the previous page. We do not reject H0. I want to make sure everybody understands what the confidence interval tells us. Confidence interval tells us do not reject H0, because H0 mu was 7, and that's H0, and it's in between the two limits. Therefore, all it does, do not reject H0. The rest of that comes as before. Then you elaborate. What does it mean you're not rejecting H0? It means the claim is true or false. If you're not rejecting H0, you're rejecting H1, the claim becomes false, and you know the rest. Let me quickly show you the t-table. Okay, so this is the z-score, negative and positive. So we are looking at the t-table. Okay. We are interested in finding the p-value. We know that degrees of freedom is 11. I want you to look at the degrees of freedom of 11 here. And go across number 11, you see all those numbers. We are looking at this row. So if you look at this row, all these numbers are in this row. What is it that we want? By the way, t equals negative 0.290. That is your test statistic. Your test statistic is negative 0.290. For the sake of the table, you go with the positive one, okay, just because it gives you the same by symmetry, right? So you're looking at 0.290 in essence. Well, it's nowhere to be found, but it's somewhere here is the idea. So if you look at the top, area in one tail. So take a look at the area in one tail. So it's somewhere here, not area in two tails, area in one tail. So look at it. The very first one is 0.005, 0.01, 0.025. And so what is the trend? They are getting larger and larger. So the last one is 0.1, corresponding to 1.363. So what is the one we want? We don't have it, but for sure, according to the table, is larger than 0.1. And that's my point. We may not know the answer from the table, but we know for sure that is larger than 0.1. And in a matter of comparison to alpha of 0.05, that's larger than that. Therefore, we get to the same result. We covered 3 different methods. All of them resulted in the same thing. So in short, traditional method compares 2 numbers, p-value compares 2 areas, and confidence interval either contains the value for H0 or it doesn't. If it contains, don't reject H0. If it doesn't, reject H0. In this page, we have various technologies that give us the answer. TI, StatDis, Excel, Minitab, StatCron, Human, SPSS, JMP. There are various technologies that they can do the job. In some cases, when they calculate, some of the values may be slightly different, but the point being, technology can always be used. But it is important we be able to do the interpretation and understand what they're doing. All right, here's the next one.
The body temperature measured for 106 subjects indicated a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Use a 0.05 significance level to test the common belief that the population mean is 98.6.
Okay, so let's see what's given. When we start, obviously we see n. with a mean of 98.2. Understand that 98.2 degrees Fahrenheit refers to 106 subjects. So it's important to see this is X bar. And standard deviation of 0.62, again, this is S because it is going back to those 106 subjects. Alpha is 0.05 and 98.6 is mu. So that's very straightforward. I spent a lot of time on the first one, hoping that that gives us everything we need to move on fairly fast with the rest of the question. So now what happens? Let's write the first step. H0 mu is 98.6. But what is H1? Use a 0.05 significance level to test the common belief that the population mean is 98.6 degrees Fahrenheit. And so it means whether it's less than or greater than, it's fine, and therefore it's not equal to. So remember, we want to see that it is 98.6 or not, and we believe that in essence that's our claim. So pay attention to the fact that why the claim goes for H0 and why it's a two-tailed test. All right. Now the next step is very simple. Calculate the test statistic. T equals X bar minus mu over S over square root of N, and we have everything plugged in. It results in negative 6.642. The next one is the critical value. Degrees of freedom is 105, and the table gives you plus minus 1.984. If not, the degrees of freedom is not there, you have to go with the degrees of freedom that is closer to the number you want. This is due to the fact that it may be limited. So having said that, we are comparing now two numbers. It's a two-tailed test, critical values of negative 1.984. So this is negative 1.984. And this is positive there on the right side, 1.984. So in a matter of comparison, where does this number end? It's way smaller than negative 1.98. It's somewhere here. It's to the left of this number. It's way into the rejection region. Therefore, your calculation results in reject H0. That's all your calculation does. Now you do the writing. If you are rejecting H0, you look at step 1. Claim is sitting next to H0. So you are rejecting the claim. That means the claim is false. And then you do the writing. So there is, or in this case, there is not sufficient evidence to support the claim, the common belief that the population mean is 98.6. And sometimes they write it slightly different. I want you to be exposed to that. There is sufficient evidence to warrant rejection of the common belief. It really depends on the text. Some texts like to use that type of vocabulary. Whatever course that you're taking, you follow that for full credit. I think this is more common. There is or there is not sufficient evidence to support the claim. That is more common. Now what happens if we want to go with the p-value? According to the p-value, the methodology is as follows. In the case of a p-value, you find the area to the left of negative 6.6423 and you multiply it by 2 because it's a two-tailed test. Let's look at that. So let's look at the technology. This is the p-value. That means 1.4036934 times 10 to the power of negative 9. And the reason they write it in this fashion because the number is extremely small. So that means 1.4 as I'm going to stop at 404 times 10 to the power of negative 9, which is much smaller than alpha, and you get to the same result. So two-tailed test, the p-value 2 times the area to the left of that. Technology gives you almost 0. If you go to the table, and I'm going to assume by now, after I explained how that thing works, you are comfortable with that. Try it on your own. According to the table, simply the p-value, because of the limitation of a table, you don't have an answer, but you know that the p-value is less than 0.01. So you get to the same decision. Finally, the confidence interval method. uses x bar plus minus e is t alpha over 2s over square root of n. Everything is in the previous page as far as the t, s, and n. Plug in and add up, and if you use technology, you come up with the answer of 98.081 and 98.319, which means we are 95% confident. The true population mean is somewhere in between. And by the way, notice alpha was 0.05. This is a 95% confidence interval. The reason they are complementary, we've seen it before, it's because it's a two-tailed test. So 95% confidence interval for a two-tailed test, it corresponds to the two-tailed test with the alpha of 0.05. And so what happens is that both ends are smaller than 98.6. In other words, the interval doesn't contain 98.6, so you get to the same result. So the range of values in this confidence interval doesn't contain the number. Which number? 98.6. So we are 95% confident that the limits contain the true value of mu, and the sample data appear not to support the claim or the common belief that the population mean is 98.6. In fact, if we were to go with the confidence interval, according to that, it seems to me that since both numbers are less, so the true population mean is less than 98.6 degrees.
A researcher wishes to see if the mean number of days that a basic low-price small automobile sits on the dealer's lot is 29. A sample of 30 automobile dealers has a mean of 30.1 days for basic low-price small automobiles. At sigma equals 0.05, test the claim that the mean time is greater than 29 days. The standard deviation of the population is 3.8 days.
I think it's very straightforward. All the numbers are given, okay. So what we have here is a sample of 30. So that's n. We see the first number. For that sample, the average mean is 30.1 days. 30.1 days. For 30 samples, that's what we have. By the way, this is mu, 29. Alpha, 0.05. Tested claim that the mean time is greater than 29 right away, larger than right tail test. And here's the thing, standard deviation for population sigma is given, and that's extremely important because now it means we can use the z instead of t. The first step says h0 mu is 29, h1 mu is larger than 29. Obviously that's a right tail test, and that is the claim as well. Let's calculate the test statistic. Test statistic uses the top formula x bar minus mu over sigma over square root of n. On the left side, when we wrote the given, we have it there, we just plug in. That's all we have to do, plug in. There is not much left to be done. When we plug in, it results in test statistic of 1.5855. The next thing is the calculation of the critical value. So the critical value comes from the choice of alpha, and we go to the z table, 1.645. Alpha is 0.05, z is 1.645. It's one of those common ones. And so take a look, 1.645. Now you compare the test statistic. Test statistic is either to the left of that or right of that. It's to the left, it's into the non-rejection region. No matter how close it is in a non-rejection region, and therefore do not reject H0. And because you're not rejecting H0, in essence you're rejecting H1, and therefore you're rejecting the claim, and therefore the claim is false. So you can write the rest. Do not reject H0, the claim becomes false as a result. There is not sufficient evidence to support the claim that the mean time is greater than 29 days. If you were to use the technology, so it's the z-test, stat test, z-test, you enter the data, mu, x bar, and sigma. You decide if it's right tail test, left tail test, or otherwise. As you can see, if we were to do the p-value, we are interested in the area to the right of test statistic, or 1.5855. Okay, that would be the area to the right of this, and that means the area that covers all of that. From the technology, we get 0.0564, which is larger than alpha of 0.05, and we get the same decision. Do not reject H0. By the way, the reason that it's fairly close to 0.05 because as you can see, the two numbers, 1.5855 and 1.645, are extremely close. That's the reason.
A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. She selects a random sample of 36 four-year public colleges and finds the mean to be $5,950. The population standard deviation is $659. Is there evidence to support that the claim at alpha equals 0.05? Use the p-value method.
Again, the key is to see what is given. To check the fee on the average, so that means you're checking the mean or mu, and 5,700 refers to mu. You have a sample size of 36. For those 36, you have a mean of 5,950, that means X bar. And then the standard deviation is for the population, therefore it's safe. The first step, H0 and H1. Mu is 5,700. And what is it that we are checking? Greater. Take a look at this one. That's how you know you use mu larger than that. It is a right-tail test. This is the claim. The second step requires calculation of test statistic. So you do that. You calculate the test statistic, which is sitting at the top right. Everything on the left is given. You just plug in, and it results in 2.28. Now, if we were to do the traditional method, we would have to use alpha, which is 0.05, and get to the critical value using the z-table. Fine and dandy, by now everybody knows. But this one, you basically need the area to the right, because it's a right tail test. Test statistic 2.28, and you compare it to the alpha. The area to the right is considered the p-value. So the p-value is the area to the right of z equals 2.28, and it ends up being 0.0113. Now, let's compare to alpha. What is alpha? 0.05. Which one is less? Well, the p-value. Therefore, you reject H0, and you know the rest. So reject H0, the claim is true. There is sufficient evidence to support the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. Now, what if we had a different alpha, just for the sake of argument? For example, let's say we were doing the same thing, but this time alpha was only 0.01. Can anybody give us the answer? With the null hypothesis, would H0 be rejected?
If P is greater than alpha, wouldn't you say that the claim is true, so then you would reject it?
No. I'm just talking about part A. Remember, it's extremely important that you ignore the claim completely. You look at the decision. Decision has three parts. All I'm asking is part A. Whenever you're done with part A, you can then continue, elaborate, and do parts B and C. But what is part A of your decision? That's all. Remember, your calculation only gives you part A, no more, no less. Then you continue explaining what that means to your readers. So tell me about part A only. That's what this question is asking. If alpha is 0.01, would the null hypothesis be rejected? Yes or no? In other words, A, reject H0, or fail to reject H0. Which one and why?
You would reject it?
Say it again.
Would you reject it?
You're asking me?
You would reject it.
No. So you're saying the same decision. No. What is the p-value? Isn't this 0.0113?
Yes.
When you compare it to this, which one is larger? P-value.
P is greater than it.
Alpha. Therefore, don't reject H0. And that's important for everybody to understand. Otherwise, you're not understanding the concept. The p-value 0.0113 is less than alpha of 0.05. That's why in the original question, we reject H0, done. But what I'm saying is that what if we change the choice of alpha from 0.05 to 0.01? The p-value is not changing, but the alpha is now 0.01. The p-value now is larger than alpha of 0.01. Don't reject H0. That means the claim becomes false, and then there is not sufficient evidence to support the claim. I highly recommend you go back on this question and understand what happens here. We have the question, and all we do when we do the calculation, we answer part A, everybody. We answer part A. Then we do the writing for our readers because we want to tell them what it means. And in an exam, we want to tell our instructor we understand what we just did. So what happens when alpha changes? So we need to understand the meaning of it. So this is a question I want everybody to look at it a few times. Make sure you get it. Make sure you're comfortable with the concept. So let's look at the next example.
A researcher claims that the average cost of men's athletic shoes is less than $80. He selects a random sample of 36 pairs of shoes from a catalog and finds their average of $75. Is there enough evidence to support the researcher's claim at alpha 0.10? Assume sigma equals 19.2.
So what do we have? It's just the given that I hope everybody can write it. This is the most important part. Can I write the given when I come across a question like that? So we are checking when it's less than that, that means mu must be 80. This is the sample size n. Now for those 36, sample of 36 pairs of shoes, the average was what? 75. What is that? X bar. Alpha is 0.1, sigma is 19.2, and H0, mu is 80, H1, what is it that we are checking? Less than, so mu is less than 80, which is the claim. A researcher claims. So that's our claim. The next step is calculation of the z-value. From the top formula, we come up with the answer. Here's the top formula, plug in. Gives us negative 1.56. The next step with the traditional method, alpha is 0.05. Using the z table, z is negative 1.28. Why is it negative? Because it's a left-hand test. By the way, we may have a negative 1.285 as an answer, which is normally the answer. You can look it up, that's fine. So what do? We just do the drawing and compare the two numbers. Negative 1.56, which is the test statistic. It's way into the rejection region. So you reject H0. If you're rejecting H0, then you are not rejecting or loosely put accepting H1. So you're accepting the claim becomes true. And then there is sufficient evidence to support, sufficient evidence to support the claim. And you do the writing. If I were to do the p-value, that's important for everybody to see. That's why in the previous example, I asked what happens when we change the alpha. If we were to do the p-value means alpha is 0.05. The p-value is the area to the left of negative 1.56. If I want to go with the p-value, this area would be the p-value. And clearly, this area is less than alpha. So you reject HC.
The average cost of a rehabilitation for stroke victims is $24,672. At a particular hospital, a random sample of 35 stroke victims have an average cost of rehabilitation of $26,343. The standard deviation of the population is 3,251. At sigma equals 0.01, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different from 24,672?
So this is me, a random sample of 35, that's N, have an average cost of rehabilitation of this much, $26,343, that's X bar. The population, and that's important, standard deviation for the population, sigma is known to be 3251, 3,251, alpha is 0.01. So can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different So it doesn't say less than or greater than, so it's not equal. So first and foremost, this is what's given, and n is large, meaning larger than 30. It's a simple random sample. Even if they don't say assume normality, we can continue with that thought. Sigma is given, and so the very first step, H0 mu is $24,672, and H1 is not equal to that, and H1 is the claim. That's what we are checking. The second step is using the top formula. We just plug in. Everything is there. When we wrote the given, we wrote everything. Plug in. So we calculate that as 3.04. The next one is getting to the CV, critical value. Alpha is given as 0.05. This is a two-tailed test. That means in each tail, we have 0.05 divided by 2 or 0.025. So we can find 2.58 plus minus, or better yet, really 2.575, I should say. We can look it up, 2.575. And
Professor,
so,
am I missing something, or is the alpha 0.01, or I'm not sure. In the
0.01, my apologies. You are right, 0.01. You are right, thank you so much. And so this is 0.01 divided by 2, which is 0.005. And the answer is 2.575. And in a matter of comparison, what is 3.04 comparing to those two numbers is to the right of the larger of the two, which is 2.58, which is way into the rejection region. So this number is somewhere here to the right of 2.58. Therefore, reject H0. So if you're rejecting H0, that means you're accepting H1. So we are accepting H1. That means we are accepting the claim. That means the claim is true. So there is sufficient evidence to support the claim, and then we do the writing. So reject H0. The claim becomes true as a result. There is sufficient evidence to support the claim that the average cost of rehabilitation at the particular hospital is different from $24,672. It doesn't say anything about being more or less, it's just different. Needless to say, because this test statistic is larger, probably you could have tested mu is larger than that. Here's the next one.
A medical investigation claims that the average number of infections per week at a hospital is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Use a 0.05 significance level to test the claim. Alpha is equal to 0.05, assume normal distribution.
It's important to see what happens here. According to this, the average is 16.3. It refers to mu. We have a random sample of 10. That's n. Those 10 samples had a mean of 17.7, which is x bar. The sample standard deviation is 1.8. That means S is 1.8. Alpha is 0.05. H0, mu is 16.3. And H1, what is the investigation? Is that the average number of infections per week at a hospital is 16.3. That is the claim. So the complementary event would be it's not equal. So take a look at the claim, and therefore you should be able to come up with the proper alternative hypothesis. With that being the case, now we use the top right formula to find the test statistic, which is x bar minus mu over s over square level. We just plug in, we do the math, it gives us a number, 2.46. The next step is to find the critical value. So the critical value comes from the choice of alpha. Alpha is 0.05. We are using the t distribution because sigma is missing. Therefore, we need the degrees of freedom of n minus 1, which is 10 minus 1. It's a two-tailed test, alpha of 0.05 in two tails. The result is 2.262 plus and minus. Therefore, if we do the drawing and comparing, this is what we get. So now what happens? Compare the location of test statistic to the two critical values. It's way into the rejection region on the right side, everybody, way into the rejection region. So you reject. What do you reject? You reject H0, and then you elaborate. Now you go look at H, look at the very first step. If you're rejecting H0, then you're rejecting the claim. The claim becomes false. There is not sufficient evidence to support the claim. Or, this is another way, I put this on purpose so you see in case if it's slightly different how you put it. There is enough evidence to reject the claim. I'm giving you different wordings because it really depends on the text that you're dealing with. So one more time. Normally we would go with there is not sufficient evidence to support the claim. There is not enough evidence. There is not sufficient evidence. But in this case, you may see there is enough evidence to reject. That's why I put the reject in red. So I want to highlight that, the difference between the two. And in essence, we are giving the same sentence. Let's look at one more example.
An educator claims that the average salary of substitute teachers in some school districts is less than $60 per day. A random sample of 8 school districts is selected, and the daily salaries in dollars are shown. Is there enough evidence to support the educator's claim at alpha equals 0.10? Assume normal distribution. And then there's the list of numbers.
Again, it's simple to see what is given, those numbers. You can calculate the information by hand or use a technology, and the technology gives you that. And so therefore you can write the given n is 8, alpha is 0.1. You can see that. And now from the calculation, you see that x bar is 58.875 and s is 5.0832. I want to show you this one. I'm going to call it number 1 and I'm going to call it number 2. When you put it into a TI calculator, it doesn't know whether you're dealing with a sample or a population. It gives you 2 answers. The first one is for a sample. The second one is for a population. This was a sample and you know that. So you make a decision that the answer is the first one. Why we are given 2 answers? Because the calculator doesn't know it's a sample of a population. You do, and so you pick up the correct answer. Now we have that. Step 1 is very straightforward. Mu is 60, H0, and H1 mu is less than 60, which is a left-hand test and the claim. That's your first step. Your second step is calculating the test statistic. That's a very straightforward and simple process. Using the top formula, you can come up with the answer. You just plug it. That's all you do. And you get to the answer, which is negative 0.624. Now, critical value, alpha is 0.1. T distribution, T table, you need degrees of freedom of n minus 1 or 7. So from the table or technology, you end up with negative 1.415. So if you do the drawing, what happens in a matter of comparison, test statistic is way into the non-rejection region. So this is your critical value class, and this is your test statistic, and it's way into the non-rejection region. So all your calculation does, it says, do not reject or fail to reject H0. That's what your calculation does. Now you do the writing. So do not reject H0. What does it mean? That means you reject H1 loosely. That means the claim becomes false. And that's the idea. So there is not sufficient evidence or enough evidence to support the claim that the average salary of substitute teachers in that school district is less than $60 per